Hello, welcome to the video. And in the previous video, we saw some curves of actual speed over time. And we saw that if the error is greater, then the slope of this curve is also greater. And when we have a very small error, then the slope of this curve is also small. And we also saw the behavior of this box. And from this, we could tell the nature of this box. So the actual speed is, as we said, basically nothing but the integrated version of the error. And we will use this principle to derive the negative feedback amplifier. So basically, in this video, we will first look the definition of integrator. And it simply says that if there is a non-zero input to the integrator, and if the input is positive, then the integrator will go on increasing the whatever the input we have. And if the input is negative, then it will go on decreasing the input. So the rate of the integration also depends upon the amount of difference or the amount of error. And as we had our desired speed, so what we are targeting over here is we have our actual speed. We are taking the difference, which is our error, and we are giving it to our integrator. And as we said, if the error is positive or the difference value is positive, then the integrator will increase the actual speed. And if the error is negative, so the integrator will basically reduce the actual speed. And the integrator will only stop when the actual speed is equal to the desired speed, or basically the error over here is 0, and it will give a steady state response, or basically it will give a constant value. So now let's look at the amplifier using this negative feedback loop. So we said that we have Vi, and we need our V naught to be K times Vi. So let's assume that Vi is a DC quantity, and as of now, let's quantify it as a DC voltage, and we have to compare the actual output to the desired one. And now actually output is V naught, and the desired output is K times Vi. So the error will be basically equals to the desired output minus the actual output, and this value will give us the error. Now there is one obvious flaw in this theory, that if we already have K times Vi, then why would we make an amplifier at the very first place? Because the main reason to make an amplifier is to make the output K times Vi. So basically we don't have K times Vi, but we do have Vi, and we also do know that we have output of V naught. So the feedback system is basically trying to make our V naught equal to K times Vi. So we can say that we are trying to make V naught by K equal to Vi. So this is how we can define our negative feedback loop, and we would like to make our V naught by K equal to Vi, and thus we would like to make our error look like V naught by K minus Vi. And now we are defining our error in a proper way without any flaw. And now we are not actually comparing actual output, but we are comparing the function of the output, and it is basically V naught by K, where K is our gain. And when we look at our error now, so we have our error V naught by K minus Vi, or vice versa, Vi minus V naught by K. So now our negative feedback loop will somewhat look like this, and we have our V naught, and we pass it through a system which will give us at this point the function of V naught, which is V naught by K. And basically getting V naught by K from V naught is very easy using a resistive divider. So let's say we somehow use a resistive divider over here of resistors K minus 1 times R and R. So at this point we will be getting the voltage V naught by K, and which will provide as a negative feedback. So error will be basically nothing but Vi minus V naught by K, and that's how we defined our error. So now let's say our Vi is 1 volt and DC, and our K or our gain is 5. So we will get V naught by 5 as our feedback, and we know, let's assume that V naught by 5 is lesser than 1 and Vi is equals to 1. So the error is basically greater than 0 in our case, and thus we will say that output will go on increasing. So now if error specified by this quantity equals to 0, the output V naught becomes constant, and error being 0 implies that Vi minus V naught by K equals to 0, or Vi equals to V naught by K. So basically, this is exactly what we wanted. So now we will see the behavior of negative feedback amplifier under different conditions. So for dimensional consistency, we need to add this factor omega u, and its role is very crucial, and we will see in our upcoming concepts and topics. So we have our negative feedback loop over here with a resistive divider for V naught by K in feedback, and the integrator integrates the error voltage VE. Now we can write a function V naught is equals to omega u times integration of VE dt, where omega u has dimensions of frequency. And after defining this function for our integrator, let's take a numerical example to make it simple and understand it better. So let's say we have omega u equals to 1 gigaradian per second, or let's say it is 10 to the power 9 radian per second, and assume that the input of the integrator over here, for this example, let's say that it is constant with a value of 1 volt, and V naught basically starts from the value 0. So basically, while analyzing it, let's say that V naught at time t equals to 0 is 0, and now our V naught from the equation we derived for our integrator basically is omega u integrated of V times dt. And as we integrate this value by taking V equals to 1 volt, our V out comes to be 10 to the power 9 times t. And if we plot our V naught against the time t, we can say that at 1 nanoseconds, our V naught is basically 1 volt. At 2 nanoseconds, our V naught is basically 2 volts, and so on. And it will increase as a ramp starting from 0. So if VE is a constant, so the input to the integrator is a constant, then V naught will increase as a constant ramp with a slope of omega u. And for example, if we decrease the value of VE from 1 to 0.5 volt, again, let's keep it constant. So the ramp will decrease with a slower rate or lesser slope, or let's say lesser omega u value. So this is the ramp for V equals to 0.5 volt, and this is for V equals to 1 volt. So this is basically the behavior of integrator, and here we have assumed the constant VE to define the just define the behavior of integrator. So now our omega u basically describes the integrator and tells us how fast or slow the output will rise when we apply VE to the integrator. So omega u is a proportionality constant, and if we use larger value of omega u, V naught will increase with higher slope, or let's say it will increase more drastically, or we can say V naught will be increasing with higher speed. Thus the speed of integration is given by omega u, but also the V naught or V output depends on omega u as well as the input voltage. So we will put this integrator now in our negative feedback system, and let's see how it behaves. So as of now, we have discussed the behavior of our integrator, and now after putting it into a total negative feedback loop, we have to see how it behaves. So we have our Vi at DC, we have the input to our integrator, which is VE, which comes from Vi minus V naught by K. And we have our resistor divider as well, and our V naught comes out to be omega u integral VE dt. Now we need to find how V naught behaves with time. So basically what we had was V naught equals to omega u integral, and we know that VE is nothing but the difference between the two inputs to the comparator over here. That's how we are taking the difference basically. So we know integral Vi minus V naught by K dt is what we are expecting in our formula. So this can be solved easily if we are writing the same equation in a differential form. So this is the same equation written in a differential form, and this equation will give us the behavior of system or V naught when VE is not equals to 0. So let's say for a constant Vi or a DC Vi, after rearranging this circuit like this and integrating it, so what we will get, like what we will get basically is, after integrating the circuit we'll get minus log of kvi minus v naught at the values v naught at 0 to v naught at t equals to omega u by k times t at t 0 to t equals to t. So after solving this, basically we will be getting this kind of equation, and let's divide this equation in two parts, part 1 and part 2, and let's see this equation and let's interpret what it has to be said. So in the part 1 we have the v naught at time t equals to 0 multiplied by the exponential, and in part 2 we have our actual desired value times 1 minus the error in that desired value, which is also a exponential. So let's interpret this. So this equation says that the initial condition of the output decays with an exponential and desired output grows as an exponential. So for simplicity, let's take omega u as 10 to the power 9 radian per second, then our k as 5, and plot the v naught versus t graph or curve. And now let's take vi as a constant 1 volt DC, and thus our desired value kvi becomes 5 volt, and which is marked over here. Now we know that at t equals to 0, v naught becomes 0, as in this case part 1 is 0. How it is 0? Because v naught is 0 at t equals to 0, and that's why when t equals to 0 we have only part 2, and also the exponential value becomes equals to 1, and part 2 also becomes 0. So we have at t equals to 0 is 0, and now at t equals to infinity the exponential part becomes 0, and thus when it becomes 0 and this becomes 0, so this total term becomes 0, and kvi times 1 remains, and that's how we say that at infinity v naught or v out basically goes to our k times vi, or basically our desired value. So this is how our graph will look like, and over here we considered that our v out at t equals to 0 starts from 0. So if that's not the case and our v out is already at 2 volts and start from 2 volts at t equals to 0, then the curve will look like this, but it will asymptotically go to infinity, and at t equals to infinity it will asymptotically reach the value of kvi. And now we have to see that how much time does it take to reach the value kvi. So basically kvi in our case is 5 volt. So how much time will it take, or how much time does this transient response occurs? So firstly, it never becomes exactly k times vi, as the exponentials never become exactly zero, and they will go towards the zero asymptotically. So still we can make an estimation where v naught reaches very close to 5 volts. So let's take a case where v naught at t equals to 0 is 0. So basically v naught is starting from 0, and thus when we say that v naught is 0 at t equals to 0, so basically this part becomes again 0, and v naught, the value or equation of v naught remains to the part 2, and we want this part which is to be equal to 99% of kvi. So let's say we want it to be 99% of kvi, so which means that if we want this part to be 99% of kvi, and we know that here we have kvi, so basically we want this part as 99%, or if we consider this one, we want only this part as 1%. So now when we put the values of omega and k, so our t comes out to be 2 log to the base 10 k by omega u, and value of 2 log base to the 10 is nothing but 4.6, and that's how we can say that nearly within 5 time constants v or v naught will reach the value 99% of kvi. And now let's put the value of k as 5 and omega u as 10 to the power 9 radian per second, and this will give us the t to be 23 nanoseconds. So thus we can say that with v naught at t equals to 0, 0, v naught reaches from 0 to 99% in 23 nanoseconds. And now we can say that the faster integrator means higher value of omega u, and as omega u increases, the time taken to reach the steady state decreases, and that's how the circuit is faster. So if we need high speed op amp, we need to use higher omega u integrator, or the integrator with higher omega u values. And I think that's all for this video. Thank you for watching.